Hey guys, it's 6.3 quadratic applications. So it's your favorite. We're doing story problems again. So hopefully you have lots of practice by the time we get to the test. All right. So this basically is telling us that there's different parts of a parabola that can tell you certain piece of information, and you will need to know each of these to be able to interpret the graph. Okay, so it's going to tell you some words, and there's key words that will help you know if it's talking about intercepts or the vertex. So let's get started. Okay, so let's draw a little graph. We can do the same graph for all of them, actually. So I'm just going to draw those really quick. These are a parabola. It can be any parabola. Okay, but what we're really looking for, that's a really bad parabola. Let's do something like that. Okay, that's still pretty bad, but anyways, y-intercepts. So we know where the y-intercept is, but when they talk about words that you want to look for are things like height. At what height does the rocket start? Okay, the start of the rocket, or here it says at what height is the rock thrown. So this is where it started. That's where the rock is thrown, if that makes sense. Okay, so you want to look at things like that, starting, those type of words. Okay, height is a y variable. Okay, so whenever we talk about height, we're talking about y. Whereas x-intercept, like here, where it crosses the x-axis, we are talking about time or distance. Okay, those are x variables. Okay, so for example, some of these key words, at what time will the ball bounce off the ground? Okay, so the time when it hits ground, that would be an x-intercept. At what time will the arrow hit the ground? Okay, what time hits the ground? Okay, that's what we're talking about. After how many seconds, that's time, how many seconds does the rock hit the lake? Okay, something like that. The seconds, how many long does it take to get to the water? So the water would be like your 0. Okay, so those are types of things that we're looking for, is time or distance. Okay, then for the vertex, here would be our vertex, and it would also be the same vertex for our y. But here we're looking for things like time or distance. So it's kind of the same thing as we do for the x-intercept, but we're looking for the time or distance that is the maximum or the minimum height. Okay, so for example, after how many seconds does the rock reach its maximum height? Okay, or here, how long does it take to reach the maximum height? So anything that has the word maximum height, that's where we're talking about vertex. And since it's talking about height, that is going to be x. Okay, or if it was time, it would be x. All right, for y part of the vertex, we're still talking about a maximum or a minimum, but we're talking about just the height. Okay. All right, so maybe I should clarify this. X part of the vertex is the time or distance that gives you that height. So when I talk about maximum height, I really should be focusing on seconds. How many seconds does it take to get to that height? Okay, that's our time. How long does it take? How long does it take to reach that maximum height? Whereas the y part, that gives us our maximum height. All right, hopefully I didn't mess that all up. but what height does the rocket explode? Okay, and we'll have a problem that talks about rockets that explode at their maximum height. Okay, so just to recap really quick, y-intercept, that is height. So usually we would have something like height for our y. And then this would be x, our x-axis. Would that be like time or distance? Okay. The x part of the vertex is the time that it takes to get to that vertex, the highest height. Okay. And then the y part is this part. It is the maximum or minimum height. Okay? Hopefully that makes sense. This is just from there to there. Okay? All right, so let's do some examples. It says a rocket. Okay, first, example 1. Using the graph to make predictions and estimates and estimate key features of a given scenario. Okay, so we're just going to estimate, do our best by looking at the graph to come up with key features. A rocket carrying a firework is launched from a hill above a lake. So here's maybe a hill. I'm just going to color that in to make it look like a hill. Okay, this is our hill. And then over here we have a lake of water. And we're going to shoot a firework up into the sky above a lake, okay? The rocket will fall into the lake after exploding at its maximum height. So our maximum height is right here. All right, it's our vertex. It says, the rocket's height above the surface is modeled by the parabola below. All right, so question 1. At what height does the rocket start? All right, so our height where it starts will be right here. It'll be 80. Okay, 80 feet. All right, how high is the rocket after 1.5 seconds? So our x-axis is time. Okay, so this is our time in seconds. So 1.5 is right here and would go up to see the value at that point. Okay, and that would be 140 feet. All right, approximately. Okay, at what height will the rocket explode? All right, well, they already told us that the rocket will fall into the lake after it reaches its maximum height. Okay, so it explodes at the vertex. So we want to write down what is the height of where the rocket explodes, which is the vertex, or the y value for our vertex. Okay, so that here you can estimate. I would say approximately 145 feet. Okay. And then how long will it take the rocket to hit the lake? So that is where it reaches its x-axis, which is here at time equals 5 seconds. Okay. All right. And I should say this. I should also say this. Okay, when I drew this mountain, or not mountain, hill, it says, and it's over a river or a lake, and I kind of drew a lake. I can't really draw that there because this x-axis is time. It's not really showing this is not like a location where it's going to hit the lake or anything like that. So, just if that makes sense. Okay, so this is time, this is height. Okay, and where it lands, This isn't showing where it lands. This is just showing at what time it hits the ground. Okay? All right, so let's go do another one. A rock is thrown from the top of a tall building. So here's our building, okay? And the distance in feet between the rock and the ground, t seconds after it's thrown, is modeled by the parabola below. Okay, so this is time. This is not where it's landing. Okay, this is not. It's not landing like whatever this we're going to estimate is not how far it lands from the building. It's how long it takes for it to hit the ground. So if you were on top of a building and you threw a rock just right here, it could just fall straight here, and when it finally hits the bottom, that could be that time where it hits the ground, 4.8, I don't know, something like that, okay? So let's answer these questions. At what height is the rock thrown? Okay, that would be when time equals 0. Okay, what is the height at time equals 0? Well, that's going to be, we could estimate maybe the height would be maybe 380 feet, okay? And a really good way to write this, because that, I don't know, that could be a line, but that would probably be fine to write it that way. But say this is y, which is our height. It's a function of time, okay? So when we are doing this problem, we're doing where time equals 0. So if you plug 0 into this function or this graph that we drew, at 0, it's going to be this point at approximately 380 feet. Okay, so that's the height of the building. It says, number 2, how long after the rock is thrown is it 370 feet off the ground? Okay, so if you drop it, this is where it starts, is maybe 380, and we want to see at what point it is where it drops, where the height is 370. Okay, so we look at our graph, 370 perhaps is about right here. So this line here is 375. So it's going to be a little less than that tick, okay? So we could drop a line all the way to the bottom, and we can estimate about here is the time where it hits. So let's say that is going to be maybe approximately 0.8 seconds. Okay, so it takes less than a second for it to drop from 375 to 370, or sorry, 380 to 370. So that's believable. Okay, and then how high is the rock after 3 seconds? So we look at 3 seconds, and we'll go up to this point, and it says that it's dropped to 225. 225. So y at the time of 3 seconds is equal to 225 feet. Okay? If a person is walking underneath the building 6 seconds after the rock is thrown, will the rock hit the person? Okay, so at 4, it's about right here. All right. And you could say at that exact time, the height is about 100 feet. Okay, maybe a little bit more. So at that exact second, at 6 seconds, would it hit a person? Well, you would say at that exact time, no, because a person is not 100 feet. So there's no way that the rock can hit that person at that exact time and hit that person. If that person didn't move and it kept falling, then yes, eventually it would hit the person, but at that exact second, 4 seconds, it would be no, because no person is greater than 100 feet tall. Okay. And then it says, how long does it take for the rock to hit the ground? All right, and we kind of put a mark there already where it hits the height is 0. The time is perhaps approximately 4.8 seconds. Okay, and all of these are pretty estimates, and we don't know exactly because we don't have an equation. Okay, and we could come up with an equation, and you'd actually be able to figure this out. And perhaps you do that in physics when you take that class, but we will not be covering that. Okay, so there is another problem. 3. The path of an arrow shown, or an arrow show in the air. The path of an arrow show in the air that doesn't make sense, but the path of an arrow can be shown in the air by modeling the function here. Okay, so now they give us a function. So the path of an arrow can be shown or modeled by this equation. That's probably a better way to say that. Okay, where y is the height in feet and the arrow above ground is x seconds after it's released. Okay, so you could say x is a time and y is its height. And what I would do is I would graph this. Okay, I could do this and I'll do this in class. And if you have a hard time doing this, come and talk to me after school. But you would want to plug this into your calculator. You could do it without, and perhaps I should do it without. Okay, so we have a vertex because this is vertex form, which is 4, 142. Okay, so it says what is the maximum height the arrow reaches. Okay, and that will always, when we kind of talked about this on our first page, that the y of our vertex will always be the maximum height. Okay, so we know the maximum height is 142 feet. Okay, that's as high as the arrow reaches. After how many seconds does it reach that height? So that will be our x value. That's how many seconds it takes to get to the 142 feet, or 142 feet. So that would be 4 seconds. All right, and then they ask, how high will the arrow be at 6 seconds and also at 8 seconds? Okay, so if you have this in your calculator to graph, all you have to do is when you're at the graph, you click trace, and then you can plug in 6 and enter. Okay, and it will tell you the height, and then you can enter 8, enter, and that will give you the height at 8 seconds. Okay, but if you don't have that, what you need to do is you will plug this in for our x, and that will give us our y value, which is our height. Okay, so if you do that, let's do that here, minus 3, oh, sorry, darn it, sorry, 1 second, go back, there we go. Okay, sometimes I bump that and it switches. Okay, so we got -3, we plug that in, 6 minus 4 squared plus 142, and you simplify that, that gives us -3 times 4 plus 142, and you end up getting 130 feet. Okay, so at 6 seconds, so y at 6, that gives us 130 feet. Okay, and then you could do the same thing with at time equals 8. That gives us -3. 8 minus 4 squared plus 142, and you can just put that in your calculator, and that gives you 74 feet. So y of 8, so the function at 8 seconds gives us 94 feet. Okay. And about what time will the arrow land on the ground? All right. So to find that, it would be really nice to have your graphing calculator. But if you don't, let's see. Trying to see what a good way, because when I did it, I used my graphing calculator. What you would need to do is you would plug 0 in for what, or no. Yes, you would plug y equals 0 into your equation. Like this, and then you would solve for x. So we're basically saying x is 0 when it hits the ground. So we need to find, or sorry, y is 0. So like if you had a graph, let's kind of make a graph of this. It's shot from 94, okay, we kind of figured that out, and maximum height, actually maybe that's not, I graphed it and that's what this looks like. 142 comes down and hits this point. So we want to have a point of y equals 0, and that will tell us, we'll actually have two solutions. One will be negative, and that would be like negative time, and so we wouldn't want to use that point, but we want to find the point that would go here. So you would solve for that. You'd move negative 142 to one side equals negative 3x minus 4 squared. Then we'd divide both sides by negative 3, and then we'd square root both sides, and then you would add 4 to both sides. So if you want me to show you how to do that, let me know, and maybe I'll do it in another one. I just kind of messed this all up. Okay? I don't want to spend too much time. So hopefully you have your graphing calculator for the test, and you won't have to worry about it. Okay? If not, that's the way you do it. 4. A ball is thrown into the air. Okay, go back. Okay, it's thrown into the air, and the path of the ball is represented by this equation. Okay, so here you would maybe want to graph it. That would make it the easiest way to do it, but if not, we'll do it the long way. Okay, so where h is the height and t is time. Okay, at what is the ball's maximum height? So here we have it in vertex form again, which is nice for this. So we know at time 4, at 4 seconds, the height is 16. Okay, and here we don't have units, and next year I'm going to change it so that there's units. But that would be your vertex. So what is the maximum height? It would be 16. And if I could, I would put feet in there for units. Okay. How long does it take for the ball to hit the maximum height? Well, that's going to be our x value for our vertex. Would be 4 seconds. All right. And then how high will the ball be at 5 seconds and 2 seconds? So what you're going to do is you'll just plug in height at 5 seconds equals negative 5 minus 4 squared plus 16. And then you just simplify. So that gives us negative 1 plus 16 equals 15. Okay, so there's 1. And then h, the height at 2 seconds, you'd plug that in, 2 minus 4 squared plus 16. Simplify that, that gives us negative 4 plus 16 gives us 12. All right, and at what time will the ball bounce on the ground? Okay, so we'll do the same thing. We know that y needs to be 0, and we want to solve for time. So we want to solve for t. T minus 4 squared plus 16. Subtract 16 from both sides. A bit more room up here, I do. Awesome. Okay, and then we need to get rid of this, divide both sides by -1. So now we get 16 equals t minus 4 squared. So now we'll square root both sides. That gives us plus or minus 4 equals t minus 4. And then we'd add 4 to both sides. So we end up getting t equals 4 plus or minus 4. All right? So, that said, you'd have two solutions. You have one that would be 4 plus 4 is 8 seconds, or 0 seconds. And here, we want it when it bounces. So at t equals 0, the ball hasn't even been thrown yet. So we wouldn't want to use that. We'd want to use 8 seconds. Okay? And then hang on 1 second. Pause. So look at my 6.3. All right. Okay, I hope I'm doing the right problems. Oh boy. Hang on. So, I'm looking at the wrong one. Sorry, 1 second. Still have the wrong one. Okay, all right, I am remembering now. Okay, so that's about 6.3. We have 3 more problems to show, but we have our next class. We're going to be talking about quadratic models on a calculator, which will also be doing story problems and things like that. So I think we're going to stop at that, and then maybe for 6.4 I will do that using a graphing calculator. Okay?